Good morning, here yet again for another session of CENG 3325 Structural Analysis. This is going to be part one of the 22nd lecture in the video series, and in this part we are going to discuss the theory of linear superposition for beams. So, and for deflections and moments, etc., in general. So, linear superposition. First I want to talk about maybe some very generic theory of what I mean when I say linear superposition, if you're not familiar with the term. And this is going to be sort of a review or a study of basic engineering system response theory. So when I say that a system responds linearly, what do I mean by that? So a linear system, who here has heard of a linear system? Anyone all heard of something like that perhaps? What I want to get at is a linear system. What does this mean? Well, in engineering parlance, a linear system is one where the input and response are linearly related. Are linearly related. And let me discuss what I mean by input and response. So a system here, in this kind of thing, and when I say system, that's an incredibly broad term. I can use the word system to refer to almost anything. But some systems have linear responses, some systems don't. For example, if I were to, let me go to basic physics. Let me give some examples from basic physics. One system that would not respond linear, something that would not respond linear, something that would not respond linearly would be something like nonlinear systems. Let me give you some examples of this. Nonlinear systems would be things like, oh, I don't know, maybe light intensity versus distance. If I double the distance from a light source, what happens to the intensity of that light? What happens to? Does it go down to half the previous value? You square the change. So if you, again, this is just a review from basic physics, there's the inverse square law, the 1 over r squared relationship. So if you double the distance, you will cut the intensity by a factor of 4. If you triple the distance, you'll cut the intensity by a factor of 9. Many field forces obey this kind of relationship. So gravity obeys this, electric force from point charges obeys this. All of our kind of inverse square law field forces follow not a linear but an inverse square relationship. So that is not a linear system. Now, so that is something that follows a very predictable but still non-linear system. And then we have many systems that are not linear, or not even that, are not linear but are not that predictable at all. Or, for example, they don't follow any very clean, simple relationships. So, for example, anything involving sociology. Anything involving human populations is going to be a very non-linear system. If you, for example, if you, I don't know, any kind of input and response on a population, whether that be, I don't know, the unemployment rate versus a politician's popularity, or the, I don't know, the, here's a good example of something that actually be very, very easy to measure. What about, for example, the amount of current lottery jackpot versus the amount of people buying tickets? That's not a linear thing. When the jackpot is 50 grand, there's a couple people buying tickets here and there, but when it gets up to 500 million, people go nuts and buy tickets left and right. That is not a linear system. You can't just plot a nice straight line from one end to the other and predict exactly. So it's a very chaotic system. Anything involving economics is a highly chaotic system. When you have, I don't know, that's why the stock market tends to go in wild swings up and down, because people are emotional animals. They respond to things non-linearly. When they, when the stock market loses, if the stock market loses 20%, if the stock market loses 10%, there's a good chance it's going to lose 50% because people see the market going down. Everybody panics and rushes for the exits and prices go to the floor. Same kind of thing. These are non-linear systems. So when we talk about linear systems, we're looking at things that have very simple, direct relationships between input and output. So linear systems. Examples of this would include things like forces. Elastic forces is the main example we're going to be looking at. So let me give maybe I'll put this under heading of linear systems. Linear systems are things like elastic forces. Remember in basic spring theory from high school physics, F equals kx. We don't even need to get into formulas involving modulus elasticity and things like that. We can look at even very basic springs. Here, if I say F equals kx, this might be your input and your response. For a simple ideal spring, if I double the force that I apply to it, I double the displacement I get from that. Again, if I double the force, I double the displacement. If I triple the force, I triple the displacement. This is a purely linear system. If you want to talk about, if I wanted to give an example of a human-centered system that would be linear, maybe hourly work, if for someone making hourly wages. Now, if you're salary, it's a bit different, but for hourly, I cannot say hourly properly, like the owl, like the animal, great. Hourly wages. Yes, so if you're making a fixed amount of money per hour, if your pay rate is $10, $15, or $20 per hour, there is a very direct linear relationship between the number of hours worked and the amount you get paid. So again, the amount you're paid would be your rate times time. Very simple. Something that'd be nonlinear would be something like, I don't know what you make versus if you're on salary or something. Well, then maybe if you, maybe if you're working at a salary position and you work really hard and you do really well, maybe you'll get a big bonus at the end of the year if you're lucky. But that's not a direct linear relationship. There's not a very clean, direct relationship. It's more about, anyway, that kind of thing. So this is the basic idea between linear and non-linear systems. And so why am I talking about this? Why is this important? Well, linear systems have an interesting property, and that is superposition. So linear systems allow superposition. In other words, okay, so what this means, or what does this mean, superposition? This is a very fancy way of saying that, now of course you can go into the theory and there are entire texts written on system response theory, but at a basic level what this means is, or for our purposes anyway, what this means is that our inputs and responses can simply be linearly summed. And responses can simply be linearly summed. So you may recall back in, again, I like to bring these things back to like, oh, I don't know, things like high school physics and stuff, because I do like to sort of relate things back to the basics when I can. For example, consider wave theory. This could be electromagnetic waves, this could be the waves, even the waves on physical waves, like the waves on the surface of a pond or something. Or pressure waves in an atmosphere, seismic waves, whatever they may be. Let's say, do you remember how waves can constructively or destructively interfere with one another? So let's say two waves are coming along, and one wave front looks like this, and another wave front looks like this, and it's going like this, and another wave front is coming along, and it also looks like this. So, you may remember from high school physics and such that when two waves interact, they simply can, their responses, their shapes, can simply be summed. So what you end up with is constructive interference, in this case at least, because this one will line up with this one will line up with this one, the peaks and the troughs will line up with each other. At the instant where this point is lined up with this point, you'll get a summation of the two, something kind of like this. Simple summation of the two responses. They can just be added together. Or you can also have destructive interference. You can also have destructive interference. For example, if I had maybe the opposite, let's say I had something like this, maybe something like this one coming in, a wave like this moving to the right, and the opposite wave, something like this, moving to the left. At the instant these two overlap, we're going to end up with basically no wave present on the surface. It's just going to be just a zero height wave right at the middle, or approximately zero, because this peak here is going to cancel out this trough. This trough is going to cancel out this peak. That is destructive interference. This is constructive interference. And destructive interference. So in other words, in more general terms, if you have, let's say your inputs, let's say I are inputs, and your R's are your responses. And your R's are your responses. Well, what you can say is that the I total is just I1. Let's say you have a series of I's, and you have a series of R's. I1, I2, I3, for example. R2, or R1, R2, R3, for example. And maybe your I total is I1 plus I2 plus I3, or sorry, I should probably do this responses here. R total, your total response, is equal to the sum of the individual responses. But you can also say that this is equal to, because these are linear, there is some constant of proportionality, K, relating them. So this would be RT, or R1, would be equal to K times I1 plus K times I2 plus K times I3. Or I could also just say that R total is equal to K times I total. Again, in cases where everything is linear, you can simply add up the inputs and the responses, and they will all remain linear. So I'd like to next get away from so this is very general theory across many domains of physics and engineering, but I'd like to look at something more specific to structural analysis. I'd like to then next look at something much more specific just to structural analysis. So for structural analysis, really what we're adding up, let me show what our inputs are. Generally our inputs, what do you think our inputs are going to be for structural analysis? For our system? Exactly, forces. Yes, that makes perfect sense. So our inputs are going to be forces. These could be forces, they could be couples, etc. Forces, couples, loads, reactions, whatever you want to call them. And what will our responses be? Deformation, yes, exactly. So our reactions, our responses is going to will be our deformation, whether that's deflection or rotation. Deflection or rotation. So for example, the idea here, if I consider, for example, a beam. Let's look at a simply supported beam. let's say I apply 3 different loads to it. Maybe first I apply P1, and that causes it to deflect a deflection delta 1. Then maybe I apply a P2 to it, and for now look at this as being at the same point, P2, and this causes an additional amount of deflection, P2, or delta 2. It's a very crooked beam. That would be delta 2. And then next, maybe I apply P3, and I get additional deflection, delta 3. So I have these P's, and I can simply say that the delta total is equal to delta 1 plus delta 2 plus delta 3. But these subdeltas, these delta 1, delta 2, delta 3, these are the same deltas that would be produced, or same deflections that would be produced if P1, P2, and P3, if P1, P2, P3 acted alone on the beam, and P3 acted alone on the beam. So in other words, if I wanted to know the amount of deflection, and if it were, for some reason it was difficult to calculate these things together, I could just go and calculate, okay, how much will this first force cause it to deflect, how much will the second force cause it to deflect, and how much will this third force cause it to deflect, and then simply add up the deflections together. I can simply add up the combined deflections together, and that will produce the final combined deflections. And now that's not so useful for 3-point loads. Again, that's not going to be so useful for 3-point loads. But where it's really useful is where you have cases of multiple loads on a beam, multiple different types of loading on a beam. So obviously, if I just did 3 different point loads at the same point, it would be trivial just to add them together into 1 point load. But where this is exceptionally useful is where I have multiple different types of loading at different places on the same beam. So consider this for a moment. This is very useful for complex beams, or complex loadings, I should say. Very useful, exceptionally useful for beams with complex loading, and really structures with complex loadings in general. This doesn't just apply to beams, it also applies to frames and trusses. For structures with complex loading. So let's draw a nice, fun, really complex beam. So let's consider something like this. Let's draw a beam. Now I'll keep the geometry simple enough, but let's say it's simply supported, and let's go nuts with just lots of loadings on this thing. Oh, let's see. Let's say, first of all, just to get things off to a nice fun start, let's say there's a trapezoidal load on this. Not even a nice triangular load, but a trapezoidal load. Like this here. And so maybe we start at some W1 up here and decrease down to W2 here. Oh, and then let's just keep making this more and more fun. Let's say there is a P1 at this point here, and a P2 here. And maybe these are distances x1 and x2. X1 and X2, and I'm not done yet. let's say I could put a couple on this thing. Maybe there's a couple, maybe I'll just call this M1 here. And maybe this thing's at X3. What a mess. Isn't this beautiful? Isn't this lovely? Or you could have almost like a roller coaster type problem where there's just loads all over the place. Looking at this is going to be a nightmare to try to solve. Now, we could do it, but honestly, we have worked things of this level of complexity before, but imagine what it would take to do this, say, by integration. I can see that I would first need a load function that would go from here to here, but then, and that would actually not be too bad. There would be one continuous distributed load function all the way down. However, I would need, in terms of my zones of integration, I would need one from here to here, one from here to here, one from here to here, and one from here to here. So I would need 4 zones of integration. If I wanted to find the deflection by integration, I would need to do this across 4 different zones using the boundary conditions from one into the next. It would be a royal pain in the butt, which we could do, and it wouldn't be so bad. But we do have another way of doing this. Because remember, we have said that as long as things are linear, as long as the responses are linear, we can simply sum up the inputs to produce the final output. So how do we do this? Well, I'm looking at this. I think I'm going to break this down into 5 sub-beams. If I want to do this, I can actually break this down. Let's say I'm interested in finding the deflection. Let's say I want to know what is delta as a function of x for this whole beam. Well, what I could do is I could go and say, okay, well, let us look at this beam and say this is actually equivalent to the summation of 5 different beams. The first delta, oh, maybe that would be, let me draw this with 5 different beams. Here, 3, 4, and 5. Now they would need to be the same length, they would need to have the same coordinates, they would need to have the same geometry. So this wouldn't work well for a system that, for example, a beam that was tapered or that kind of thing. But as long as the length was constant and you kept the same support conditions, etc., everything would work nicely. So maybe the first one would be my distributed load. Oh, I want to get a nice constant distributed load here. Constant-ish. With values or magnitude W2 and W2, then I could have the linear portion or the decreasing portion here that goes from well, it would not be W1, it would be basically W2 minus W1 because I want to get just the triangular portion of the load there. W2 or W1 minus W2, like that. W1 minus W2. Then I'd have another beam with the point load P1 here. I would have another beam with the load 0.2 here. And then I'd have my moment beam, or my couple beam. And for each of these, I could then find an individual delta function. So I would get delta 1 equals some function of x. So that's some function. And I could get that fairly easily. Delta 2 as some function of x equals something. Delta 3 equals some function of x equals, again, some function. Delta 4 is some function of x, and that equals something. And delta 5 is some function of x, and that, again, is something. So now, at first glance, this might seem, okay, well, what is the advantage of this? How am I making my life easier? Now, instead of solving one equation, I have to solve 5. Why would this be any easier? I don't have to drive 5 sets of equations instead of 5 integrals. I don't see the difference, right? It might at first seem like there's no benefit. But the real benefit of this is that you're able to use pre-calculated, pre-derived formulas. So let me show you something. I have a file already pulled up, and this comes from the AISC Steel Manual. So you can find these in most structural analysis texts. You can find this in these tables that I'm showing you come directly from the AISC, American Institute of Steel Construction Steel Manual. And so, but you can find what we call beam tables in many different kinds of references. So your structural analysis textbook, if you don't have those, likely has a set of beam tables. Most mechanics and materials texts have them. The ASC Steel Manual has them. You can find them anywhere online. Just search beam deflection tables and this kind of thing will pop up. And so notice what you have here. You have a series of formulas derived and calculated for very simple types of beams. This particular one, for example, is a simple beam with a concentrated load at the center. So that would not necessarily be appropriate for our cases here, because here we didn't have loads at the center, we just had them at some unknown position. But I could use case 8 here, a point load somewhere at the center, somewhere that's not along the center. And I could use this formula here, feeding in my known quantities into there to very easily get a deflection as a function of x. Then I could, for the, let's see, we could find maybe others. Okay, here we go. Well, I don't see my, this table is trimmed a bit. I would want to get the simply supported beam with a constant load across the top. Actually, no, here we go. Simple beam. Do we have a uniform load? Yes. So for the first beam, I could use this, the simple beam uniformly distributed load. I could use the formulas there for this load here. For the linearly increasing load, I could use this one here, although I would have to flip it to have compatible directions, because this one assumes the load is increasing to the right when it's actually increasing to the left. So then, and for my moments, there should be a formula for one of these for couples as well. And if not, we could find, if not in this one, we can find it in other references as well. But it may be in there. I'd have to go and do a search. But if it's not in the AISC manual, you can of course find it in other ones, or this particular one. If you have to derive one or two of them, it's usually not too bad. So again, you can use pre-derived formulas to calculate the individual deflections, rotations, or internal moments for any of the ones you produce. And so that's going to get you a couple delta x's. Now, what you will have to do is, you will have to do the same kind of resolving of boundaries that we have when we've done the virtual work. So we'll have to resolve boundaries. Because these are going to give difference. So for example, this delta 3 of x, I called this one delta 1, or x1. So for example, on your delta 3 of x here, you had a p1 and an x1, and we would have some delta 3 of x function. But this is gonna, if that's x1, we would have some piecewise function of some function and some function when when x is less than x1 and 1 when x is greater than x1. And each of these functions, or at least anything with a point load or a point moment, for the case of the distributed load, or the uniformly distributed load, or the uniformly decreasing load, the continuous function, those wouldn't have subzones. But for the case of any kind of point force or point moment, you're going to have different bounds of integration. And so you're going to have to resolve those before you add your different functions together. So we'll still end up with a final function that's of similar complexity to what we looked at previously. But I can tell you, if you are allowed to use these formulas and you have them, it's going to be a whole lot quicker and simpler to use pre-derived formulas than to reinvent the wheel every single time. So again, the basic idea, once you have this, your delta total, your overall delta as a function of x, is just going to be equal to delta 1 as a function of x, plus delta 2 as a function of x, plus delta 3 as a function of x, plus delta 4 as a function of x. And you can see where this is going. Delta 5 as a function of x. So again, you can simply sum up the responses produced independently by each individual input. The final response is the summed responses of each individual input. Of the responses of each input. And also critically, this doesn't have to be simply constructive interference. Loads can often destructively interfere with each other. So for example, if you have, for example, destructive interference in the example of deflection, so destructive interference can occur. For example, if you have a, let's consider the same beam with two loads on it. And let's see, if I have, let's say I have a point load and a couple applied at the same location. Well, the couple, well, let's look at the deflection caused by the point load. The point load deflection is going to be fairly simple. The point load deflection is just going to be a nice, friendly, simple thing like this, deflection downward. And the couple is going to be a deflection, something like this. We're going to end up with an inflection point in the middle. So something more like, kind of like this, in a way. We're going to have, this is going to want to cause things to twist to the left here. And so, basically, on the left side of the beam, this would constructively interfere, but on the right side of the beam, this would actually actually destructively interfere. So, you'd end up with a final deflection that is exaggerated on, that is much greater on the left side than the right side. So, you'd end up with something greatly exaggerated here, but more like this. Something kind of like this. And actually, I should probably show it, I wanted to show it smaller on the left-hand side, or on the right-hand side than it was before. So something kind of like this, greatly reduced. All right, questions on this so far? Okay, again, this is just general theory. Now, I also want to discuss where can we use this. So, when can we use this? When can we use this? Well, the key word here is linear. Linear. And in civil engineering, mechanics, materials, and structural engineering, there is something that should, when you think linear, what do you think?
Elastic.
Exactly. When I hear the word linear, I think linearly elastic. So, linearly elastic. That fundamentally is what linear means in the context of civil engineering. So, again, if I go back to my good old stress-strain diagram, if I have strain and stress, we know that stress-strain relationship generally follows a curve, kind of like this. We start out linear, and then eventually we top out, and then we go into yielding. And we usually approximate it like this. In truth, we do get some strain hardening before fracture, but usually for analysis or for design, we just simply say, okay, let's just consider it yielding at the constant yield stress indefinitely. So, but anyway, that does for this particular discussion, that doesn't matter. What does matter is that we are keeping ourselves not just in the elastic zone, but in the linear elastic zone. So we are below epsilon yield. So this method is appropriate as long as your stress remains below the elastic limit. This method works only as long as your stresses are below the elastic limit. Your stresses and strains are below the elastic limits. Below the elastic limit. So if your strain is greater than the yield strain, or if your stress is greater than the yield stress, you're no good. You can't use this method because your system no longer responds linearly. And so again, when you're at that point, there are ways to analyze those structures using those structures and beams using what we call plastic analysis, but you cannot analyze them using this very simple linear approach. So this is the same kind of assumption we're using with virtual work or when we assume small deformations. It's all the same basic stuff. We're assuming linear systems, and if we don't have that, then we have to use other methods. You have to use things like finite element methods. You have to use things like plastic analysis. There are more advanced tools that you can use, but you can't just simply do a simple summation of your loadings there. All right, any questions on any of this? Yes?
So when you're summing up the deltas, is there a way to find like the resultant X location where the most of it would be accumulating?
Okay, the question is, going back here, when you're summing up your deltas, is there a way to find the location of the maximum delta? Well, the way you do that is simply via differentiation. You take the derivative of it. Or you could find where the curvature, if you want to know where the maximum there is, you could just find the curvature function or the slope function. And because you know that's the derivative of the deflection, where that's 0, this is the deflection will be max. So really the only way to do that is to use your mathematical tools. If you have now you'd have to take the derivative of each of the pieces, each piece of your, yeah, it can be tedious, yes, each piece of your bounds within each bound to find the actual maximum, but that's how you do have to do it. Or alternately, you could plot it. If you have a function, if you have a nice plotter function, if you have a nice plotting tool, computer plotting tool, you can take your function, plug it in there, and simply plot it, and then look graphically at the maximum, or at least use that to find where your maximum deflection would be, et cetera, et cetera. Okay, other questions? Good question, but other questions? Okay, that'll do it for this part of the lecture. Thank you for watching. Thank you for bearing with me, and hope you've learned a bit here. That'll do it for now, and as always, thank you.